Hello, I'm Puri Ali Nejad, and in this video I discuss Oran principles and architecture. I will start with introductory topics and I will conclude this video with the Oran architecture. Here in Visio, I draw every piece of Oran architecture step by step, and we will follow these steps until we reach the big picture here. Okay, let's go back to the presentation slides. So at the first step, let's see who started Oran and who are the participants. The main organization for Oran standards is the Oran Alliance. It started at February 2018 by AT&T, China Mobile, Dash Telecom, NTT Docomo, and Orange. And there are other elected members which will be changed each 2 years. Currently in 2021, Bharati Airtel, Dish Network, KDDI, Rakuten Mobile, Reliance Jio, Singtel, TIM, Telefonica, Verizon, and Vodafone are participating as elected members. And there are currently 10 active working groups and 4 focus groups in Oran Alliance. It's a good idea just read their names as it gives you overall view of the matter, and you will see some new words and acronyms which will be addressed later in this course, like the A1 interface, E2 interface, and other interfaces, non-real-time RAN intelligent controller, and the near-real-time RIC RAN intelligent controller, the XHAL, and about the focus groups, standard development, test and integration, open source, and security focus groups. Next one is Telecom Infra Project, or TIP. It was formed by Facebook in 2016 and have members like Nokia and Samsung Research America, which are among top RAN vendors. Open RAN Alliance focus is on standardization, but TIP focuses on implementation, which includes creation of high-level technical requirements for use cases, testing and validating the network elements, products, and configurations, and then sharing best practices for commercial deployments of these tested technologies. Actually, TIP have other work groups, and Open RAN is just a part of TIP tasks, which is followed as a work group. Now, let's talk a little bit about transmission network. As you may know, in Cloud RAN, we have the Fronthaul interface, and transport network is divided to Fronthaul, Midhaul, and Backhaul. And again, as you know, Fronthaul is the connection between radio unit and distributed unit. And this transmission network needs to be cost efficient and support strict latency and jitter requirements. There are different solutions for Fronthaul, such as SCF NFAPI, Network Function Application Programming Interface, eCPRI, Enhanced CPRI, Common Public Radio Interface, IEEE 1940.3, NGFI ROE. Actually, it is IEEE 1940.3 Task Force, which designed radio over Ethernet for encapsulating in-phase and quadrature IQ data to be carried on the Ethernet, and IEEE 1940 workgroup standardized NGFI interface, which later divided into NGFI 1 and NGFI Part 2 for Frontal and Backhaul, and TIP vRAN Frontal. And we are not going to talk about details of these transmission standards. You can just look them up in the internet. And about this NFAPI, a small cell Froom tried to standardize it to connect small cells to a centralized unit. Next one is Open RAN Policy Coalition. In 2020, some policymaker, equipment vendors, and service providers decided to make widespread Open RAN deployment possible. So they started to negotiate with governments and make regulatory bodies required tools. Finally, in April 2019, the Oran Alliance set up an Oran Software Community, OSC, to develop open source software for Oran solutions, and open source softwares patented and developed in a collaboration between OpenRAN and Linux Foundation. Moreover, collaborations with GSMA and NGMN and ONF, ETSI, 3GPP, and some other organizations are made to be aligned with other industry bodies and to ensure compatibility and to avoid duplication of work. The key objectives of Open RAN includes these 4 topics. The first one is preventing vendor lock-in. To avoid vendor lock-in, we need interoperability between various RAN components and also hardware and software disaggregation in RAN. Because in this way, the operator can choose between RAN manufacturers. The Oran Alliance's primary goal is to help create a supply chain that opens up the RAN market for new vendors. So the work is founded on the principles of openness, so different vendors' products can interoperate without close cooperation between vendors. Market competition is the second benefit. Currently, big and well-known companies like Nokia, Ericsson, Huawei, Samsung, and ZTE have over 80% of RAN market share. So if RAN becomes open to more vendors, there will be more competition, and this leads to lower CapEx costs. Enhancing network features is the third benefit. Previously, if a vendor decided to limit R&D investments and remove some features, then the operator couldn't purchase it from others. But by making RAN open, it's possible to buy various features from various vendors. So overall, improving CapEx and OpEx is possible by increasing competition and using techniques to enhance network performance. Let's go to next slide. To start talking about Oran's architecture, we first need to lay the ground by discussing legacy networks and evolution towards 5G. The image is from ITU and it have 2 legs. In 4G leg, you see we have CPRI as frontal and S1 interface in backhaul. Also remote radio head or RRU, RRH, it depends on the vendor to name it, and the BBU, or also called system module. By moving to the 5G leg, you can see that BBU is split to centralized and distributed units. You can see layer 2 and layer 2 non-real-time functions and layer 3 functions are moved to centralized unit, and layer 2 real-time functions and part of layer 1 is moved to distributed units, and the rest of layer 1 functions remained in RRU. And also some user plane functionalities are moved to CU and DU, which resembles, for example, edge computing to reduce latency by making the data closer to the user. Let's now take a deeper look at the split options which are considered by 3GPP and OpenRAN SDOs in next slide. In the upper flogram, we see bus uplink and downlink directions and RAN protocol stack from PDCP RLC to physical layer. Here, as you see, physical and MAC and RLC layers are divided to higher and lower parts, and based on the split point, the options are written here from option 1 to option 8. Based on previous page and the image for 4G leg, we can have the Fronthaul interface, CPRI interface, between the BBU and RRU or RRH, and BBU contains most part of the protocol stack and RRU just have the RF part. It's like the option 8 split. In the next line, we see that we have the option 2 split, and the CU have PDCP and RRC layers, and the other layers reside in the DU and RU. It's called high layer split, and it's a split on the Mid-Hall F1 interface. In the next line, we see option 6 and option 7 splits on the higher or lower physical part between MAC and physical layer, or between physical layer higher and lower parts. This is called low layer split, and it's in the Fronthaul. And in the last line, we have a combination of bus option 2 and option 6 here, or option 2 and option 7 here. In this way, CU, DU, and RU units each contain a portion of protocol stack. Also note that setting the split point with less physical functionality at the DU here reduces the requirements on transport network on Fronthaul. And if we set the RU with low compute capability by choosing a low split point, it makes it simple, reduce its size and weight and power consumption. So determining the functional split of physical layer is an important design choice, since the choice of physical processing responsibilities and where to put them have a major influence on both the transport network and RAN components. Here you see real-time functions are deployed near the antenna site to manage air interface resource allocations, and non-real-time control functions are hosted centrally to coordinate transmissions across the coverage area. For example, cell utilization prediction function. And here, if we move to lower layer splits, it will have better coordinated multi-point performance, while higher layer splits will be more delay tolerant. Here we have everything on the DU distributed unit, and here we have everything on centralized unit. When everything is on centralized unit, we can manage things from higher layers, and when everything is in distributed unit, it means we have faster access to the distributed unit and it will be delay tolerant. Frontal capacity requirements for different functional splits. The frontal bandwidth depends on the exact split point between DU distributed unit and RU radio unit. The figure compares the frontal bandwidth requirements for a 6040 64R massive MIMO with 100 MHz bandwidth. And you can see that in split 6, physical layer is completely implemented in radio unit. This option requires 3 gigabits per second link. And option 7, we have 3 types of option 7 depending on the point of split in the physical layer. In the option 7, the physical layer is split between MAC and RF part, and some part of physical layer is also added to the distributed unit, and the remaining parts are added to the radio unit. The bandwidth changes between 4 gigabits per second to 140 gigabits per second. Here, split 7.3 and 7.2 seem more realistic because they keep the massive MIMO and beamforming in the radio unit side. Split 8, where the physical layer is completely implemented at the distributed unit side, seems more impractical because it needs an eye-popping 236 gigabit per second link. It's enough for the presentation slides. Now we will move to the Visio file to check the architecture. Here. Okay. Here, Visio is a little bit slow when I zoom in and zoom out. So let's continue on the PDF file format. It's easier to move between slides. In this image, you see the functional architecture proposed by Oran Alliance. It's not complete. We will make it complete in subsequent pages. You see that step by step we will add more details to this diagram. Okay. You see radio unit, Oran's distributed unit, Oran's centralized unit, control plane, and user plane part. And in this model, Oran control and user plane are disaggregated to add flexibility to the architecture. Also note that this O prefix in ODU, ORU, OCU is almost the same as the ones that we discussed in PowerPoint slides. So ORU is the normal RU radio unit. It's just shows that it is Oran's defined radio unit. This O cloud, I write it here in blue in the background. It means that these functions ODU, OCUCP, and OCUUP, all of these are implemented on O cloud, Oran cloud. It's a platform made by a collection of physical infrastructure nodes that meet Oran requirements to host these relevant Oran functions. And also there are other functions, we will discuss them later, like this near real-time intelligent controller. This one also can be implemented on the O cloud. And this O cloud also needs to support software components like operating system, virtual machine monitor, container runtime, and other management and orchestration functions. Therefore, here the Oran network functions can be VNFs, can be virtual network functions. It means virtual machines or containers can be installed on this O cloud. Also, these can be PNFs, physical network functions with customized hardware. Okay. Also, here we can see interfaces towards core network, OCU control plane towards the AMF, access and mobility management function, which receives connection and session information from user equipment. And here OCUUP entry interface towards user plane function, UPF, which handles many aspects of routing, forwarding, and tunneling. This image shows the Oran Alliance choose option split 7.2 because this is the optimal splitting point in terms of RU complexity and transport network loading. And it's, as we see in the Xilinx and presentation, it's somewhere between the physical layer, and we will add more details in next page. So let's go to the next page. Here, let me zoom in. Here, the physical layer split in option 7.2 leads to the physical layer to be splitted such that IQ decomposition, precoding, IFFT, and CP addition, D2A conversion, and analog beamforming reside on the ORU radio unit part, and the rest of the physical layer tasks, including scrambling, modulation, layer mapping, precoding, resource element mapping, and IQ compression, reside on the audio side. Then this frontal interface between ORU and ODU have 4 functionalities, including C planes, control planes, U planes, user plane, sync planes, synchronization plane, and management plane. In this synchronization plane, we need to know that synchronization information is not transmitted with enhanced CPRI on Fronthaul, but we are using synchronization protocols like SYNC-E and PTP. And this user plane carries data in IQ format, in quadrature and phase format, and this control plane will support configuration of this radio unit. For example, for scheduling, beamforming setup, precoding, support for dynamic spectrum sharing, and symbol numbering and symbol duration. And next, Oran configurations will be carried on this management plane. For example, we can say software management, installation management, and configuration management are carried on this management plane. There are also other examples like file management, fault management. And later we will see that the management plane is also optionally connected to the SMO unit, but have it in mind, later we will see it. You see in next slide, you see here we have an O1 interface here and open Fronthaul management plane here. Later we will talk about it. It's optional for now to connect it to service management and orchestration controller. But for now, the management plane is considered between ORU and ODU. Later, we will have another management unit connected to other orchestrators in Oran's architecture. There are also other interfaces in this image. Here we see the X2 interface. You know it. It's between 4G and 5G. It's also the interface between 4G and 4G nodes. And XN interface between two 5G nodes, okay, and F1 interface, F1C and F1U, F1 control plane and F1 user plane, and E1 interface. And this F1 interface is mid-haul, and it exchanges data about frequency resource sharing and other network features. And this OCU can communicate with ODU via these F1 interfaces. This E1 interface connects to disaggregated OCU-CP and OCU-UP functions, and it transfers configuration data between these two planes, between CU and CP part, and the main information is the capacity information from user plane and also the status of the user plane. Okay, so the control plane can know the status of user plane through the E1 interface. Let's move to the next slide and add more details. Here we have this little box here. You see that we have EC-PRE and radio over Ethernet protocols for Fronthaul interface, for control plane, and for user plane and control plane on top of the UDP and IP. Let's move to next slide. Here we have more details, and the high-level view of Oran architecture consists of the network functions, a service management and orchestration framework, SMO, to manage the network functions, and an OCloud that hosts the cloudified network functions. This SMO is responsible for managing and orchestrating the multi-vendor and disaggregated Oran network functions, such as this near real-time RAN intelligent controller, OCUs, and ODU. And also here it have a connection to ORU. We will talk about non-real-time and near real-time RAN intelligence controllers later in next pages. And here we just want to talk about interfaces. Four key interfaces are A1, O1, here we have O1 interfaces, Open Fronthaul management plane, and O2 interface. And all of these O1 interfaces are connected to SMO, and here we need to know about XApps to talk about O1 interface. Okay, here I added a short description of the XApps, and you see that O1 is connected to our all network functions, and for ORU I draw it in a dashed line because it's for future study and not finalized yet. And here about XApps model. It's a management model, and it's an ISO network management system. It's an abbreviated form of 5 working levels of network management: F for fault management, C for configuration management, accounting management, performance management, and security. And please read more online if you need more info about it. And this O1 interface, which is connected to SMO and network functions, uses XApps to encompass a large variety of different areas like provisioning, performance assurance, trace management, file management, heartbeat management to check availability of nodes, PNF startup and registration management, and PNF software management. And moreover, in most cases, this SMO serves as the consumer and RAN functions serve as the producer. Okay, so in XApps model, these are producer and SMO is the consumer. For example, in case of fault supervision, when some alarms are appeared or changed in ODU, it can act as a provider, and O1 interface will send these faults to the fault provisioner, which is SMO. SMO acts as a fault supervision consumer. The next interface is the E2 interface, which connects near real-time RAN intelligent controller to network functions and also 4G eNode B. And these elements combined, all these elements make an E2 node. An E2 node can only connect to one near real-time RAN intelligent controller, but one RIC, one RAN intelligent controller, can connect to multiple E2 interfaces, E2 nodes. And E2 interface just carries control plane protocols, and these are for controlling and optimizing the E2 node elements and their used resources. Also here we have one A1 interface between non-real-time and near-real-time boxes, and it's to allow the non-real-time RIC, RAN intelligent controller, to provide policy and optimization information to the near real-time RIC. We will see more details about this functionality when we talk about near real-time and non-real-time functions. In next slide, here we will talk about the remained interface, O2 interface. You see here here we talk about O1 interface, which uses XApps for management, about A1 interface, which is about policy, sharing policies and information between non-real-time and near real-time RAN controller, and E2 interface, which is for communicating, controlling information between nodes. The O2 interface remained. We will talk about O2 interface in this image, and I removed all other parts to make the image simpler. In next slide I will add removed parts. Here, let me zoom in. This O2 interface is for secure communication between this SMO, Service Management and Orchestration Framework, and OCloud. Here we have OCloud, and of course, you know, when we have cloud, the cloud has Service Management and Orchestration Framework. Okay, we have a cloud provider to provide us with the OCloud, and this cloud have infrastructure management services and deployment management services. This is about cloud. And here in the service provider side also we have a cloud. It have OCloud orchestration and management and network function orchestrator. This O2 have two main roles. It's divided to two parts. It's actually one interface, but it's divided to two parts to show that it have two main tasks. And the main one is to management of the OCloud infrastructure. You see it's connected to the OCloud infrastructure. And it consists of scaling, healing, health check, diagnostics, and provisioning, deployment, and termination of different tasks and virtual machines on the OCloud, and deployment of lifecycle management of Oran cloud-native applications and cloud-native functions that run on this OCloud are shown in this part, which include administration, scaling and scale-out, infrastructure discovery, XApps, and platform software management. Now, let's go to next picture. I'm going to make sure that nothing remained here. Okay, let's go to next page. Okay, at the 5th page, we have more detailed parts in non-real-time RIC. Here, we have non-real-time RAN intelligent controller in SMO system, again, Service Management and Orchestration Framework, called SMO system. There are control loops. You see a control loop here at various levels, and they run simultaneously. Depending on the use case, they may or may not interact with each other. Here you just see one control loop. In next pages we have other control loops. Here we have another control loop on near real time and another control loop on distributed unit. But for now, just concentrate on the first control loop, on the near real-time RAN intelligent controller. Okay, we will talk about other control loops later. It takes 1 second or more for non-real-time RIC to execute its functions. We will talk about its functions and applications. This non-real-time RIC is a logical function. It means it is software and it is not hardware. And it only connects here to the near real-time RAN intelligent controller, and it provides necessary information for RAN optimization, and this information includes policies, data, and machine learning models, and they are carried on the A1 interface. These policies are used for enforcement, and machine learning models are used to make decisions based on network's current context. This A1 interface enables communications between two RICs and supports policy management, data transfer, and machine learning management. The data, which is actually called enriched information, here we have policy and enriched information, okay, is actually for assisting the model training for the AI and machine learning in the near real-time RIC. So we have some data, enriched information to help near real-time to run its AI and machine learning algorithms. And here we have some R applications. Near real-time RAN intelligent controller applications are named R applications. These R apps will make RAN control algorithms more innovative by making RAN systems development much faster than its current pace with current vendor proprietary systems or centralized SON methods. Let's see some examples on these R apps in the next slide. Okay. Here we have some example R applications. The first one is future location prediction, the second one is cell utilization, and the last one is UEQE estimation. The first R application can take related data to UE's current serving cell and any available neighboring cells from the GNodeB CU. You see here it's connected with O1 interface to OCUCP and OCUUP. Okay, so it can have this information and do signal analysis and use the positioning data from the serving and neighboring cells to predict future locations and mobility patterns. The second, let me move. The second R application, cell utilization, can perform trend analysis to predict future cell utilization by using future location prediction and cell utilization services. And the last one can provide UEQOE estimation from device's current cell and future cell after handovers. We will see more suggested sample applications in next pages. Okay. And here, as you see, these control loops require more than 1 second. Future location prediction based on the neighborings and current cell is an algorithm that takes more than 1 second to gather the data and return the results. Okay. Now, let's move to the near real-time RAN intelligent controller. We talked about non-real time, and it's time to talk about near real time. As mentioned in previous page, non-real-time RIC takes 1 second or more to execute its function, and here this near real-time RIC takes between 1 second and 10 milliseconds, more than 10 milliseconds and less than 1 second to execute its functions. Its control loop is somehow faster, and its applications, which is named X applications. In non-real-time RIC we had R applications, here we have X applications. Its applications reside between the near real-time RAN intelligent controller and network infrastructure, here the ODU, OCU, and OCU, CP, and UP. This RIC, near real-time RIC, directly controls and optimizes the low levels of RAN using AI and machine learning for automating the process. AI and machine learning also are useful to decide when to enforce policies that control routing and quality of service. Here also we see that we have quality of service management. There are many sample suggested applications. Here you see the list. Sample suggested applications for XApps and RApps. It's good to read their names. Context-based dynamic handover management for vehicle to everything, V2X. Dynamic radio resource allocation for unmanned aerial vehicles. Traffic steering, quality of service and quality of experience, QoS, QoE optimization. Massive MIMO beamforming optimization, RAN sharing, QoS-based resource optimization, RAN slice service assurance, multi-vendor slice performance management, dynamic spectrum sharing, and network slice subnet instance, NSSI resource allocation optimization, and local indoor positioning in RAN. The use cases for non-real-time and near real-time control loops and the interaction between the RICs for these use cases are completely defined by Open RAN use case analysis technical specifications. And here, if I go to the Oran's page, I currently made them ready. In the specifications section, you can see all Oran's specifications, and if you search use cases, you can see a bunch of specifications here. You cannot directly download them. You need to push this button and fill in some information to have access to them. I did it, and now I can download them, and I downloaded 2 samples. Here you can see Oran workgroup 1 use cases detailed specification, have some use cases, flight path based dynamic UAV radio resource allocation for UAV applications, QoE optimization, traffic steering, massive MIMO beamforming optimization, RAN sharing, QoS based resource optimization, RAN slice, and all other things, dynamic spectrum sharing, about slicing, and local indoor positioning in RAN. I think the last one was this local indoor positioning in RAN. Okay, so you can take a look at this document. We are not going to talk about it. It's very detailed, and you can read each use case one by one if you are interested. Okay, also there are other specifications for use case report also for A1 interface and non-real-time RIC. I downloaded it also. Use case and requirements for non-real-time RIC and A1 interface. It also includes some other use cases for QoE, QoS, context-based dynamic handover management for V2X. Okay, later please take a look at these documents. They are fruitful documents. And also there's one white paper, Oran Use Cases and Deployment Scenarios white paper, February 2020. It's in the resources part, resources, here in resources branch. And again, I downloaded it, it's here. It's about, again, it's about some possible use cases and their scenarios. Okay, you can later take a look at it also. QoE optimization, traffic steering. It's very direct to read them. You now know the basics of Cloudrun and Oran, and you can just take a look at them. It's easy to understand. For example, this image, OEM logical architecture. Now you know the ODU, ORU, and the interfaces E1, F1, E2 interface, A1 interface, O1 interfaces, and also the O2 interface for OCloud management. We've talked about all of this, and here you see the non-real-time and near-real-time RAN intelligent controllers. Okay, later you can take a look at these documents. Let's go back to our presentations. No, to our PDF file. Let's go back and talk about XApps. These XApps are made of XApps images, and these images are software package coupled with the XApps descriptor, which describes the packaging format. These XApps will run as a collection of microservices deployed within a Linux container environment. And XApps process the data that is gathered from E2 interfaces. Here you see these E2 interfaces from DU, CP, OCPO, CUCPO, CUUP, and also I forget to draw it. It should be connected. It's not here, but E2 also is connected to E node B. Okay. And the 6 XApps use data gathered from E2 interface nodes in order to support near real-time radio resource management, and their output is often designed to change one or more configuration parameters to optimize a specific metric related to access control, and also maybe other metrics like as bearer control, handover control, QS control, resource assignment, and other possible metrics. Here also you see that we have radio network information base. It's a database, and it contains actually 2 databases. One database holds UE information and another one holds radio network information. And the data are configurations relating to E2 nodes and cells, bearers, flows, UEs, and mapping between them. Here also we have XApps subscription management. Where's my mouse? XApps subscription management. And you know that these XApps need onboarding, deployment, resource management, and termination. And overall, it's better to say they need lifecycle management, LCM. And we know that LCM is a function that is performed by SMO, SMO, Service Management and Orchestration Framework. But here we need also an XApps subscription management here to ensure that the LCM tasks that are assigned are fulfilled. Okay, we need to know that everything that comes from the SMO is down and fulfilled. And the next one is management services here, which also covers the XApps, and it allows the appropriate XApps data to be shared with consumers such as SMO. You remember we said XApps have consumer and producer. Okay, so here it will produce some data to SMO as a consumer. And we have other boxes like security to provide some security functions, messaging infrastructure, which is suggested by Oran Alliance that near real-time RAN intelligent controller should have a messaging infrastructure, and also some other parts like shared data layer and conflict mitigation, for example, for providing logging, tracing, and metrics from non-real-time RAN intelligent controller to SMO, and also solve or support conflict resolution between the XApps, maybe two XApps at the same time need to change one configuration, but this conflict mitigation will manage the conflicts between different XApps. For example, imagine that QS management wants to increase the cell size, and at the same time interference management wants to reduce the cell size. Then a conflict happens in the results of these two XApps, and conflict mitigation needs to resolve this issue. Okay, we are down here. Let's go to next picture. I also added two small boxes here in all cloud orchestration and management part of SMO, because it's a cloud. It should have policy, configuration, design, and inventory parts. Okay, I just write them to make the Visio file more fruitful. Okay, and now we finished talking about Oran architecture. Okay, we talked about physical layers, the and the Fronthaul and Fronthaul interface, and how physical layer is split between layers. And here we have the last control loop on DU, which is really near to the UE, and this control loop takes more than 10 milliseconds. I think I write it wrong, it's less than 10 milliseconds. Okay, I will edit this one. It needs less than 10 milliseconds to execute. I will edit this and I will upload this Visio file and the PDF file on the internet. Later you can find it and use it in your presentations, or maybe you want to edit some parts of it. Okay, and they split two on the mid-haul, different interfaces here, O1 interface, O2 interface, E2 interface. All of these are discussed. Also interfaces to our core network, XApps for O1 interface. And let's go up. Here we talked about SMO and non-real-time RAN intelligent controller. We talked about near real-time RAN intelligent controller and RApps here and XApps here. And this is the end of this course. Just one R1 interface here remained between our applications and non-real-time RIC framework, and it is just used to send and receive data from non-real-time RIC framework, and also this RApps will subscribe themselves when want to start their task at non-real-time RAN intelligent controller. They need to subscribe and tell that they are ready to start their work, and tell what are their required data and what are their outputs and what is their signature. Okay, I don't see anything remained, and this is end of this course, and thank you for watching this video. You can also subscribe to my YouTube channel with my name Puriya Ali Nejad for watching future videos. And for any questions you can contact me on my LinkedIn account, or using my email on my LinkedIn account, or also my phone number is open. And thank you and bye. I hope to record more videos on new technologies and edge technologies. Thank you. Bye.